All right, welcome Xuan Zhong again with the re-recording. Xuan is engineering manager of audio signal processing on autonomous vehicles at Zoox. He got his PhD with Bill Yost at Arizona State on the topic of dynamic spatial hearing by human and robot listeners. And since that time when he was working at Google, he also presented several chapters of this book at the internal Googler course that we ran there. Thank you so much for volunteering, Xuan, and take it away.
Thank you. Today I'm presenting chapter 5 of the Human and Machine Hearing book. Starting on the next slide. So over the years, I've been working on the multiple generations of audio perception systems on the robotaxi platforms, both at Waymo and now at Zoox. So next slide is showing some of the applications that I think would be important in the future. So far, there has been a comparatively limited application of machine hearing systems. But that may change in the future as more and more service robots come into our everyday life to help us do the cooking, laundry, as well as plumbing. So as there are more robots, the field of machine hearing would be more important. And the next slide is showing the overview of the whole book and where the chapter is at. So I have the habit to try to visualize everything. And here is what I call a machine hearing fairyland. So each of the color represent a different main section of the whole book, starting with section 1 of sound analysis and the representation overview. So I may click on this, so you can see that chapter 5 actually is the very last chapter of the whole section. And to me, it serves two purposes in the whole book. One is to set the stage for the next section on the system theory for hearing about why it is important. Actually, it may be a good idea to come back to the chapter after you finish that whole section. And in addition to that, if you can click one more time, it's also heavily related to the core of the whole book, which is our CARFAC. In section 3 is the auditory periphery, and the CARFAC is a very effective and effective audio feature with a very rich representation of sound. So that is how the current chapter 5 is related to chapter 15, which I'm also volunteering. So the details is covered in the next slide, which shows the table of content for the whole chapter. So we start with the different sound types and the audio features that people developed for all these applications over the years, including speech and music, as well as their arbitrary sounds. And then we go through a array of audio features starting from section 5.2 all the way to section 9, covering a wide range of audio features, also with the influence of the auditory models. And that is toward the end we summarize with a general ASR technique, as well as their improvements needed when we are processing more complicated sounds. So the next slide is showing the key question that we are asking in this chapter, which is probably also a question that many of the audience ask themselves. So which audio feature should I use? If you go to any for a decent survey of the audio features, you can see there are probably not many hundreds, but at least there are quite a few dozen of audio features that people explored over the years with their various degrees of success. And the answer is that it depends. It depends on the kind of audio signal that we are processing. And the chart on the right is showing the different applications. So over the years, many researchers in the audio processing domain have been developing a wide range of applications, features for speech and the music. So this is most of it is called the acoustic approach. But now, as we are moving towards a general solution of the machine hearing problems, we are targeted not only at speech and music, but also arbitrary sound forms in general. So that is called the hearing approach. Starting with the next slide, with some more details for the acoustic approach. We are trying to model the acoustic of sound sources about how things are generated. And later on, we will take a speech as an example. So this kind of acoustic model describes the physical process of creating certain sounds, such as a speech. And over the years, it is somewhat influenced by auditory perception theories, such as the inclusion of critical bands or some kind of frequency compression. The hearing approach, in contrast, is trying to model the kind of signal representation that the ears send to the brain. So it's trying to delay the interpretation into sound source features to later or higher level processes, as we discussed back in chapter 1. And its focus is on arbitrary sound types instead of just their speech and the music. So moving on to the next slide. This one is showing the short time analysis. So we cannot analyze the sound of arbitrary length that is can be infinite. So as a result, we are doing a windowed version of it. We're doing windowed segments of a sound waveform as shown on the picture to the right and at the top panel. So in this one, we have I believe, just a speech signal, probably just a vowel. And on top of it, you can see there are two example bell-shaped window function, and these are separated by a hop. So here, the window is a Hamming window of 80 millisecond, which is typical for speech applications, and the hop size is 20 millisecond. And as we iterate this process, you can see that over time, we are generating a total of 6 subsections of this input waveform. And the reason for using a bell-shaped window function as compared to a simple segmentation is that when you are doing the latter case, essentially you're applying a rectangular window to the input waveform. And as a result, when you process it later in the time domain, in the frequency domain, this is equivalent to a sync function in the Fourier transform. So with a lot of issues in the side lobes. So applying something that is much more like a Gaussian filter, as shown in the Hamming window in the bottom panel here on the right, gave us a much better suppression of the side lobes in the spectral domain. So, and this one is originated from the resonator theory of hearing from I believe, chapter 2. So moving on to the next slide. So after doing the windowing, this series of temporal waveforms is then goes to the FFT for fast Fourier transform, and that have been pointed out in the book. essentially, STFT, short time frequency Fourier transform, is just like a bank of bandpass filters and with their equal bandwidth. And that is based on the mathematical interpretation of how Fourier transform is being generated. And this comes with a increase in center frequencies. But in most of the cases, actually the short STFT has a reduced version, which is a short-term power spectrum which is a reduced version of it. So as a result, we are only using the amplitude of this transformation. And at the same time, actually, we are giving up a lot of the fine temporal structures here. And when we are trying to reconstruct the output of the filter bank without the temporal fine structure, it would be it's still possible to reconstruct some of the tonal signals as well as music and some part of speech. But as soon as there are interference of multiple sound sources or lots of reverberation, this may no longer be the case. And in addition to STFT, we also have the short time autocorrelation function, which is our STARF, which we'll cover a bit later. Moving on to the next slide. So a little bit more comment on why the temporal fine structure is important. As Dick pointed out in one of the early version of this course, for example, for the direction of arrival estimation, which is essentially sound source localization, it is heavily based on the phase difference of multiple microphones. And it is also the case for human listeners. For example, the JND, or just noticeable difference, of ITD, which is interoral time difference, comes in the order of 10 to 20 microseconds. So which is essentially very close to just one sample if you're sampling the waveform at 44.1 kilohertz. So this is one example that shows how critical the temporal difference can be. And in addition to this, the temporal fine structure is also important for pitch estimation in speech, as well as their signal processing in cases with their reverberation. And for the case of detection of a siren, for example, for robotaxi applications, there are cases that are at a certain point when the noise level keeps increasing, and especially for sounds from faraway places, the signal of the siren may not be visible in spectrogram or STFT. Whether if you listen to it, because your brain is able to process the coherence of the signal over time, or being able to sense the harmonic structures, you can still hear the siren. So these are showing how important the temporal fine structure could be. So moving on to the next slide. So over the years, there have been a couple of modifications for the short time spectral analysis that was just discussed. So one issue with the STFT is that it has too high resolution at high frequencies. So there has been efforts to borrow partially the auditory filters to try to modify how these filter banks are arranged over the frequency domain. So here to the right is called a constant Q filter bank. And as you can notice, for the horizontal axis, the frequency are arranged in a logarithmic scale and not linear. So here we have a geometric sequence of center frequencies, and each channel has a bandwidth that is a constant fraction of its center frequency. So, however, towards the lower frequencies, because the way that the human ear is processing the lower frequencies, there is also some additional non-linearity. So as a result, in the constant Q filter bank, the lower several filters are also combined to mimic the behavior of the human ears. So moving on to the next slide. So here is some additional processing that is done based on STFT. To the left is what the input waveform that is being windowed by a bell-shaped function. And for the 6 output waveform, as shown in the left panel, these are related to the 6 curves in the middle panel, which is a short-time log spectra. So the issue with doing the log spectra is that you have many extreme low values, especially for numbers that is close to 0. As a result, you can see that the middle panel is also pretty noisy, but they're doing additional smoothing. As shown on the right panel, you can see that the smooth short-time log spectra is giving us a much cleaner representation of the waveforms, of the audio representations. So moving on to the next slide. So here are some examples of frequency smoothed spectrograms. And we have 3 pairs here. For each pair, the left sub-panel is the original calculation, and the right one is the one that is smoothed over the frequencies. So I'm categorizing all these 3 cases with both their spectral smoothing as well as their amplitude compression. So the left panel is showing one of the processing with no spectral smoothing. So in the left subpanel, you can see there are many white spots, which correspond to very low values or zeros. And for the compression, is also not doing much compression. So I believe it's a logarithmic compression, sorry. For the middle panel, there is a slight smoothing over the frequency. And for the compression, we're still using the logarithmic compression. The right one is probably the one that gave us the best performance. It still has the smoothing in the spectral domain, but for compression of the amplitude of the numbers, it is using the power law as specified in chapter 3. So if you compare all these figures, you can see that one to the right is giving us more contrast in high power areas. So it's more representative of the higher numbers. But meanwhile, it is also giving us less noise due to the slight smoothing to remove the lower extreme of the numbers. And overall, it's giving us better visualization. And when you put this to the machine learning systems, it's also giving us better results.
Xuan, let me comment on that for a moment. It's, I think, important to understand here that there's 2 places where we're talking about smoothing here. So on the ones that say slight smoothing, that's a slight smoothing across the Fourier transform bins before doing the logarithmic or power law compression. And then the relationship between the left panel and the right panel in each pair is a smoothing that comes after that compression. And the one on the left is what you often find in what they call cepstral smoothing, where they are smoothing the log spectrum, the log power spectrum, without any pre-smoothing before the logarithm. And that's why you see on the leftmost panel, a bunch of little white dots in there. And those basically are where the logarithm is headed toward minus infinity, because there's channels that happen to have near zero energy in them. If you just do a little bit of smoothing, those go away, as in the middle pair. And if you smooth after the logarithm, those little white dots become kind of vertical streakiness in the smooth spectrogram. So this kind of illustrates how the conventional cepstral smoothing kind of captures meaningless noise in the representation, and that you can improve that by a little pre-smoothing and or better nonlinear compression function. It's pretty subtle and complicated. There's a lot packed in here, so I can see people might struggle to study it. I can see Brian poring at his screen trying to figure out what I'm talking about. Okay, thanks.
Yeah, thanks. So moving on to the next slide. So we can also do additional processing of the transformed data. So here is a example of a dimension reduction with the PCA, principal component analysis. So here we are projecting the spatial data onto a set of base functions that capture the variance of the data. And for speech, interestingly, cosine transform actually come fairly close to ideal variance capturing transform. So the first order would be the loudness, which is not shown on the picture to the right here. The second order is the spatial tilt, starting with low frequency and more decreasing toward the higher frequencies, as shown in the very lower panel of the picture to the right. So essentially, for any smoothing or transformation, there's a trade-off between the amount of compression and the loss of details. So moving on to the next slide. So another way to look at the signal is to use the source filter model. So here, by source, we mean the for the speech applications. For the source, we mean the vocal cords that is excited at a cycle of roughly 20 milliseconds, which creates the pitch. They're related to the prosody of the speech. And that signal is further filtered by the vocal tract, which is essentially the tongue and the lips and their shapes, which changes the spectrum of the speech. So the can you click on the video in the middle? I don't think there's sounds, but this is a MRI of a talking
sondern
person.
eine Aufnahme mit der Magnetresonanztomographie oder kurz MRT, die auch als Kernspintomographie bekannt ist.
Yeah, thank you.
Das in Göttingen neu entwickelt.
That should be enough. So, which I think is a cool video on YouTube to show the real-time the position of the tongues and as well as the lips and how they related to the speech sounds. So, as a result, the speech signals spectrum can be modeled as a product of a citation spectrum and a filtering frequency response. Moving on to the next slide.
Sondern eine
So in addition to this, we also have the cepstral analysis, which is very hard to pronounce, but it's a rearranged version of spectrum. So this is called a homomorphism in the log spectrum. So this processing, the charts as shown above is similar to the STFT, but towards the end of it, after doing the logarithmic of the amplitudes, we are doing an additional Fourier transform of the logarithm of the power spectrum. So when we are doing this, so essentially we are separating the source as well as the filter. So the low frequency is representing the short time coarse structure, and the high frequency is representing the long time fine structure. And that would be discussed a bit further in the next slide. So here is the different processing of the same speech clip. The top panel is the spectrogram of the speech, and the horizontal axis is time for all the three panels, and the vertical axis for the top panel is the frequency. And when we are doing the capsule processing, the vertical axis is called the frequency, which is a rearranged version of the frequency. So here we can see a dotted line that is related to the order time of probably 2 milliseconds. And we can, on the top part of the middle panel, we can see that there is a dark line, and that changes over time. This is the pitch period, mirroring the movement of the pitch harmonics that are resolved in the narrowband spectrogram. And the part that is below the dotted line, which is the low frequency, relates to the vocal tract effects of the filter. So when we are removing the top part and keeping only the lower part, and that is called a lifted version of the original spectrogram. You can see that much of the details have been removed, and we are only keeping the vocal tract effects of the filters. So moving on to the next slide. And this processing has also been influenced over the years by the auditory approaches. So there are two issues with the capstrom analysis as is. One is that it is an overly simplified version of the processing. It goes directly from the sound to a description of the vocal tract shape. And meanwhile, it's also using unrealistic or non-linearity. So for pitch extraction of speech, as discussed previously in the power law chapter, a exponent of 0.25 to 0.67 have proved to be more robust than either linear or log. So the question here is what a sound sounds like to the human ears, instead of simply try to model the speech as a source plus a filter. And one other question is also how much compression is enough. So that heavily depends on the applications. So for human listeners, if we are talking about a normal hearing listener, so probably not much compression will be okay, because the compression will happen in the human ears anyways. But if we have a hearing impaired person with only, for example, 40 decibel of dynamic range, then we need to do the compression for them. Similarly, it is the case for robot listeners. It also heavily depends on the application. So for example, what is the dynamic range of the training set and how it compares to the test data set, as well as how loud or soft the input sound would eventually be as compared to the training data. So all this needs to be considered when we are constructing an actual auditory processing system for robots. Okay, moving on to the next section. So over the years, there has been quest for more accurate perceptual frequency scaling. The commonly used MEL scale actually has a breaking frequency between the lower frequency, which is more linear, and the higher frequencies that is logarithmic. So compared to the human auditory system, this breaking frequency is quite high. So there has also been other studies that showed a curve that is more related to human hearing by both Moore and Greenwood with a breaking frequency at 228 hertz or 165 hertz. So in both cases, the breaking frequency is much lower compared to the commonly used MEL scale, and there also provides a better representation of the special components of the signals. So moving on to the next slide. So additional processing based on the capstrom is called the MEL frequency capstrom coefficients, or MFCC, which is very widely used in the speech processing domain. And here the short time power spectrum is warped to a MEL frequency scale as discussed before, again, which is not a very favorable processing with a breaking frequency. And this is further compressed through a logarithmic non-linearity, which is further transformed with a cosine transform to captural coefficients. And to the right, we can see that the three panels are showing a processing that is quite similar to the original captural processing. So this has also been widely used in the automatic speech recognition, and over the years, people find there are certain drawbacks to it, especially when there are interference or multiple people talking. It's very hard to separate all this speech. And meanwhile, it also lacks the time-profile structure of the speech. So moving on to the next slide. So there are also additional ways to process the audio signal. So one way is to look into the several of the previous samples and try to find a best predictor of that new sample that follows. So this is called the linear predictive coding, or LPC. So this is generating a frequency domain special shape that is described by a very small number of resonances, which is widely used in speech applications. So to compute a LPC, this can be based on the short time autocorrelation function, or STACF. And which is another way to smooth the parameter of a power spectrum. And moving on to the next slide. So there has been also efforts to add additional auditory influences to LPC, and this is called the perceptual linear prediction. And it does so by distorting the spectrum according to a MEL scale, as they're discussed before. So the cube root compressing the power to be more like a spectral loudness. So, and finally, there is also the RASTA, which is a relative spectral processing, which is a bank of linear filters operating on the frame rate spectral values. Okay, moving on to the next slide. So the all the previously mentioned audio features has been applied to the automatic speech recognition systems with their various degrees of success. So for the machine hearing problems, though, we think that this aforementioned structure won't be enough. And as Dick mentioned in the book, we advocate starting with a rich sound representation and narrowing down to a speech relevant features at a later stage in order to give the system a better chance of dealing with non-speech sounds, which I think is very related to what we are looking forward to in the machine hearing domain. Okay, moving on to the next slide. So as I mentioned in the book, here we are looking at the improvements needed to better represent the sound, not only speech and the music. So there are, as discussed before, we have seen a lot of benefits for adding auditory considerations for speech communication systems. And as we are moving from the speech and the music sounds to arbitrary sound types, there will be more considerations needed for the temporal fine structures. As a result, we think that the previously mentioned audio features, especially for MFCC, which has too much compression of information, and these are not suitable for general sound representation for years of machines. And especially for MFCC, the amplitude scale is too logarithmic, and the frequency scale is not logarithmic enough. And in this case, it's omitting the pitch information and many other fine temporal structure. And previously has been research shows that actually peeling off the last layer of MFCC and just using logMel improves the performance of applications such as ASR in noise. And the pitch is somewhat represented in the fine temporal structure of logMel. So as a result, we are advocating the hearing approach, which will be discussed in the third section of the whole book. As Dick mentioned, to give us our hearing machine a chance to do what a human brains do, we must move on to a model of our auditory periphery that is more realistic in what it represents from sound, and leave behind the idea that sound can be adequately represented by a phrase spectral description. So the next slide is showing a summary table of, this actually is a new advances since the publication of the book, which is the LEAF model by Neil Seidinger. So here, the model is using a learnable front end. And the amplitude compression actually comes from PSEN, which is mimicking the human auditory model. And here, it's showing that because of the less logarithmic amplitude scale, and with a learned frequency scale that is similar to that of the human hearing, actually is getting significantly better compared to the previous audio features. So the next slide is summarizing the learnings of the audio features. To the left portion is the acoustic approach, and the right portion is the hearing approach. So we compared the different methods of STFT, MFCC, and the logMel spectrogram. And when these are being compared to the CARFAC model, which will be discussed in chapter 15, we could see that because we are using a Greenwood's map for frequency scale, and we are using a fast automatic gain control, which is a nonlinear amplitude scale, with the inclusion of the phase information. Actually, CARFAC model is outperforming all these audio features. And then moving on to the next slide, which I think is the last one. Here we have 6 minutes to cover some questions. I think my question for Dick is that has the ASR features changed since your book was published in 2017?
Yeah, it's a good question. You did mention the Leaf learned audio front end, which is it's a smallish change in that it's still basically a short time spectral approach. It doesn't incorporate fine temporal structure, but it does it does show the advantage of moving to a more auditory frequency scale and a more auditory way of doing the dynamic range compression. It incorporates the PSAN, which is a thing we developed, I think, while the book was being finished up, and published it sometime around, I don't remember, 2015 or 16 or something. Stands for per channel energy normalization, and that's basically an automatic gain control running on each of the MEL frequency channels. And so when Neil invented his Leaf approach, he basically mapped that into network layers where he could learn to optimize the parameters of it. So the system didn't learn to do Leaf, he taught it how to do Leaf and how to optimize it. So that was, I think, the largest part. His ablation analysis showed that the largest part of his performance gain came from including Leaf in there. And we did some more experiments later where we moved toward even more auditory frequency scale, because his system had the ability to learn the center frequencies of the filter channels, but they tended to not move very much from their initial conditions because it's hard to back propagate to such parameters. We showed that if we started with a more auditory frequency scale like the Greenwood map that CARFAC uses, that it did better, and it was a better starting point for the learning and so on. So these are small changes to the conventional short time spectral front end that shows some advantages. In terms of using fine temporal structure, I would say not as much progress on that, although there are some approaches that have been tried that are able to use fine temporal structure to some extent, even though they don't represent it in anything like what I would consider to be an auditory way. For example, the TASNet uses very short time analysis basis functions in a speech enhancement context. And there are some other front ends like SoundStream for audio compression that again uses very short first layer filters to basically encode time domain events more than frequency spectra. So there's a couple of examples there of things that are getting some advantage from moving to an approach that looks closer to time domain than frequency domain. But has anyone actually tried the CARFAC as a front end and showed advantages with it? I don't know. I should check the literature again. Maybe someone has by now.
Yeah, thank you. Any other questions?
I have one question. Can you hear me?
Yes.
Hi. So my question to Zhong is that when you say CARFAC model outperforms some other representations, what kind of task you did that comparison?
The task is based on general sound processing, not only speech and music. I think the idea is that in speech and music, there is such a level of redundancy, so that over the years, the hand-engineered models that we used previously was very successful for neglecting the part of the details of sounds that are not related to the sound that is being modeled, which is speech. But the CARFAC model is much more generic, and there is able to process the sound in a way that there is, as mentioned in the book, delaying the processing to higher perception levels.
When you say that model is outperforming some other representations, you use some like task, right? If you use ASR, you have what error rate. If you use speaker recognition, if you do speaker verification, you have equal error rate. So in what application you can say that model is better than others?
Yeah, I don't think we have actually any good comparisons that show net performance gain on a task. The closest thing we have is what Neil did with the Leaf front end, which is sort of slightly more CARFAC-like and showed significant gains. So that should motivate us to do more such experiments and comparisons, but we haven't done that yet. Part of the problem,
I think David.
Part of the problem there is we've only recently made a version of CARFAC that we can put into the machine learning systems and optimize parameters and so on. So we've done that as part of the Australia Future Hearing Initiative work, and so we're in a better position now to do experiments with speech or other tasks.
I think David has his hand up.
Yeah, look, if there's time, I know we're close to time, but performance was mentioned at a number of points today. And by the way, thanks, Xuan, for a great presentation. I just observed that, you know, empirical performance of classifiers is a function of the classifier's intrinsic ability to discriminate the class of inputs that's presented to it, and also the set of inputs that's presented to the classifier to be evaluated. So that, you know, those things come together. So this question about, all right, what's the task that's being evaluated, I think is a really important one. And, you know, I'm interested to know what is the nature of the performance gains, what kinds of sounds or words are becoming better recognized. I'm also interested to know how this stacks up against human listeners. And I've recently observed a test where someone was being presented with isolated nonsense words. Geez, that was hard. Yeah, it was really, really hard. So you've got like nonsense words, which are they're made up of like recognizable phonemes, but you can't leverage any additional context there. And so, yeah, maybe it's a question for further down the track, but this issue about performance assessment and what we're probing with different tests, I think is an interesting one. I don't know if there's time for reflections, but I'd love to hear them.
Yeah, it's a really good point, David. What I did in this chapter, which, you know, I literally wrote this in 2010, so it's been a while. Is I tried to survey places where people had done performance comparisons, typically on speech recognition tasks, with kind of conventional versus more auditory influenced changes. And there's quite a lot of those, and in general, they don't go anywhere like all the way to a good cochlear model, but they're making these tiny steps of changing the frequency scale and changing the way amplitude is compressed. And in general, they've had pretty positive results. But I've also, you know, I've come to realize that's all, from my point of view, that's all kind of small potatoes compared to what we're going to get by taking the temporal fine structure seriously and incorporating that, which really nobody has done other than these things I mentioned that use a kind of a more time domain approach. and those are very recent. So yeah, we need to do these things, and it's not just CARFAC, but it's CARFAC combined with ways of leveraging temporal fine structure, such as through the stabilized auditory image. So it's not just the middle part of the book, it's the one after that about the auditory brain that we have to combine in order to get to something where I think we'll see potentially big gains. We have done small experiments with such combinations on a few tasks and found advantages on pitch-related tasks because those are the ones where the temporal fine structure helps. We expect to also see advantages on things like speech and noise, but we haven't shown that yet.
Great, thanks.
I think we still have some hands up. Jinhui has his hand up, and Hongling and Abhinav. So I think Jinhui's next.
I think we heard from him already.
Oh, he didn't put his hand down. All right, Hongling, up to you.
Oh, first, thanks for the great presentation. I just want to hear more about your comments on the difference between, or on the comparison between MFCC and log-mail spectrum. To me, it seems like MFCC is more focused on detecting the formants because it's explore the periodic signals in the frequency spectrum. And for log-mail spectrum is compared with MFCC is closer to the hearing approach, but I'm not sure whether my understanding is correct, and I want to hear maybe more deeper insights about that. Yeah, thank you.
You want to make any comments, Xuan, or did you want me to take it?
No, you can take it.
Okay.
Yeah.
So when you compute MFCC from the log-mail spectrum, it's just an inverse Fourier transform. So it's linearly related. But then what they do typically in speech recognition systems is they throw away most of the higher order coefficients and they keep just the low frequency ones. So it corresponds to a smoothing of the spectrum and then a linear transform of that. And the reason they do that is because the higher frequencies are where the pitch shows up. And traditionally in speech recognition, they've wanted representations that are not distracted by talk or pitch. They just want to get at the vocal tract shape. With modern large neural nets and deep learning and so on, they can handle learning multiple examples with a range of different pitches. They don't get confused with each other the way they did in the old Gaussian mixture model systems, which had a hard time learning kind of complicated manifold of where the data should be. So in the modern deep learning systems, they learned that peeling off that final transform and truncation to low order just made things better. The first layer of course of a fully connected neural network could do that inverse Fourier transform if it wanted to. If that was the right thing to do, it would learn to do that. But I think it's not what it does. So I still wouldn't call the log-mail spectrogram very auditory, even though it does have auditory influence, which is kind of the point.
It does compare with MFCC, I think.
Compared with a linear amplitude scale, the logarithmic is somewhat auditory, but not very. And compared with a linear frequency scale, the MEL scale is somewhat auditory, but again, not very. It's not as accurate as something like a Greenwood map or the ERB scale. So we can basically go further in making the frequency scale more logarithmic and making it more realistic that way. And we can go less far in making the amplitude scale less logarithmic and use a power law and dynamic gain control to do the compression. And when you put all those things together, you get something that looks a lot more like a cochlear model, whether it's CARFAC or just a filter bank with a decent AGC.
Awesome. Thank you, Dick.
Just a further comment on that, Dick. I mean, it's kind of interesting that you know, the psychophysics tells us if you take out the fundamental frequency, humans have a lot of difficulty segregating two talkers. You know, and speech is actually quite sparse, so there's not a lot of energetic masking going on when you've only got two talkers. But we've got two talkers that have got a fundamental frequency very close to each other. There's a lot more information masking going on. There's an inability to sort out the bits, as it were. Now, whether that's harmonic grouping that we're using and then focusing spatial or non-spatial attention or those sorts of things. But, you know, it doesn't surprise me that, you know, models that pull that information out have a lot of trouble when you stick the speech back into, you know, the kind of environments that that we evolved to listen in.
Yep, for sure. Yeah, when you put, if you put a, you don't do that cup stroll smoothing and you put a more auditory frequency scale, then you resolve more harmonics of the pitch, then your pitches are more likely to show up as features in the spectral representation. The system is more likely to be able to segregate, you know, which regions of the speech go with which talker and so on. And that's been quite successful in speech enhancement, speech separation systems, having those, the ability for the network to see the spectral peaks of the multiple talkers. I still contend we'll do better yet with temporal fine structure than with just a spectrum.
I agree with you there. Dick, I've got to jump. You've still got a few more hands up, so I'll pass the conversation mediation over to you. Alrighty. So thanks everybody for coming, and a great presentation, Ron. Thank you very much.
Thank you.
Yeah, who's up? Who's got a hand up next? I don't see where the list is.
I think Honglin is next.
Honglin just went. How about Abhinav?
So my question was more about the arbitrary aspect of sound stimuli that we want to use for testing out the systems, which are like, I think David alluded that if you use just speech, then, you know, there's other biases coming in. But if you use garbled speech, that's another option. But in terms of a statistical distribution, is there one that works well for, you know, like capturing naturalistic sounds that you would draw your test stimuli from to get a metric?
I think it just depends on what the universe is that you want to operate in. There was a paper in 2006 by Smith and Lewicki that was quite influential about learning basis functions for sound from natural sound mixtures, and they separately did it for speech and for outdoor environmental sounds, and they got somewhat different results, like different filter cues and stuff like that, but maybe not hugely different. But definitely the if you're going to optimize the parameters of a system to a task or to a database of sound, it depends on what it is. I'd say you know, in the human experience, there's a lot of speech and there's a lot of other stuff, and it's probably a good idea to optimize to reasonably realistic mixture of such things.
Thank you.
Yeah, Brian?
I don't know if this was a completely misguided impulse, but I found myself looking at all the frequencies and the liftering, wanting to sort of get a sense of what that stuff actually sounded like. So if anybody knows of any sort of either collabs or workspaces that can sort of give you a sense of how these things work, playing with them like an audio engineer, that would be awesome. Also, seeing the code actually implemented would be super handy, just actually getting into the math.
So there's several systems that either generate speech or enhance speech using representations that are Mel spectrum, whether they're log or cube root or something like that, I don't recall, but they have definitely a demonstrated ability to generate high quality speech through a sort of a learned synthesizer. A fairly simple synthesizer that, you know, it's not going from text or something, it's going from Mel spectrogram to waveform. There's plenty of information in a Mel spectrogram to represent clean speech. So if your system basically trained on a prior that says we're trying to get clean speech out, the MEL spectrogram is a good enough representation of that. And even if the MEL spectrogram that you give it doesn't correspond to clean speech, it's learned to generate clean speech and nothing but. So that's what it'll generate. So generally, in that respect, they sound good. If, on the other hand, if you try to do an inverse from, say, a log MEL spectrogram of the sound of two people speaking at once through a, find a waveform that has that MEL spectrogram, that's harder and less likely to sound good without some supplementary pitch cues for the talkers. One way people have done that, rather than the inverse that I just described, they use what they call a noise vocoder, where you get the short time spectrum by analyzing real sounds, and then you generate the so-called noise vocoded sound by modulating a noise using those spectral to get something that has approximately the same short time spectrum. And back in the 90s, I think it was, when I was working with a grad student at Caltech on this, he called me up one day and he said, "Well, what do you mean the noise vocoder doesn't work intelligibly?" He says, I tried it and it's perfectly intelligible. And I said, "Okay, well, go back and try that on the sound of two people speaking at once." So he went back and called me back an hour later, says, "Oh yeah, I see what you mean. You can get one voice very robustly with very limited cues, like just the short time spectrum modulating a noise, perfectly intelligible. But when you have several voices at once, the sum of their spectra does not necessarily lead to intelligibility if you don't have the other cues that help the brain separate the separate voices based on sort of pitch as a carrier. That's why we need the temporal fine structure or some other kind of phase information to help the reconstruction. Now, if you have the complete log spectrum, not the MEL spectrum where you've binned FFT, you combine FFT bins to make MEL channels, you lose information. But if you have the complete spectrum, there's enough information there with overlapping windows that you can actually, with some iterative algorithms, you can infer a phase that does a pretty exact reconstruction. And you actually can get back the sound of two people speaking at once if you put enough computational iterations into it. There's what's called Griffin and Lim algorithm that provably converges, but it's slow and it's not great. So there's actually there's a broad range of experience of answers roughly to the kind of question you're asking, Brian.
Have people done much information theoretic work on the sort of compression ratios that you get from this stuff?
Good question. A lot of experimental work on things like rate distortion theory for voice coding. I think in many cases it's not. It's hard to characterize well how it deals with noise and multiple talkers and music and all that kind of stuff because the space of possibilities is so large.
Mm-hmm.
So it ends up coming down to just experimental work on certain corpuses. Like when they evaluate audio codecs, there's a certain corpus of music that they do coding on, and they have expert listeners that know how to listen for the artifacts on that music and so on. Any other questions today?
Just wanted to add to Brian's point about having some notebooks and collab spaces. I recall that there was one Carfax notebook floating around that I think I forget who worked on that. I think maybe Andre Van Schaik had put that up. So maybe if you have a particular shared folder or something in mind, we can start putting little experimental notebooks as we read the book and try little experiments out.
Yeah, that's a good point. Yeah, Andre Van Schaik at Western Sydney University has done a lot with Carfax and hardware and FPGA models and applications to things like speaker identification where they've gotten good results compared to some baseline techniques. I don't have the whole scope of it in my mind right now, but yeah, that'd be a good place to look for some positive comparison results. Yeah, Hong Lin and I visited Andre there at Western Sydney about a year ago, and got to see a few of the things they're working on.
Yeah, it's a great lab.
All right. Thank you all for coming. We can end the recording now. I'll stick around a few more minutes if anyone wants to ask questions offline.